In a previous video, I talked about using chemical equations to represent chemical reactions on a page. And what I want us to do now is take a look at specific types of chemical reactions. Traditionally, it's taught that there are 5 types of chemical reactions, and eventually you can kind of just break that down into 2 types of chemical reactions. But we'll take a look at the traditional 5 right now. I think the most basic idea for a chemical reaction is when stuff combines to make something new, and that's the basis of a synthesis or combination reaction. You have 2 or more species combining to make one new compound, right? 2 or more species combine to make one compound. All right. And our general form, and I think it's going to be handy to have these because a skill we're going to need later is identifying chemical reactions so that we can predict products, right? Why bother knowing what type of chemical reaction you have just to know? Well, it's important to be able to identify them so that you can predict what the products are going to be. So we're going to have a general form here, and this is of the most basic setup, where we have A plus X goes to AX, all right? Where our A is some generic and our B are some generic species. And when I say species, again, we mentioned this before, but it's just a way of saying thing. It's a sciencey way of saying things. 2 or more things combine to make one thing, all right? And B is also going to be some generic species. So we're going to look at some basic combination or synthesis reactions, and we're going to look at some special ones towards the end. At face value, the synthesis or combination reactions are some of the easiest, but as you look deeper in at like combining water with nonmetal oxides, you get situations that aren't super intuitive. And along the way here, we can practice our chemical reaction balancing. So we'll start out with something about as simple as it can get. We'll look at maybe hydrogen and bromine reacting to give HBr. All right, so a few strategies I want to look at, or a few key things that I want to highlight here. The number one mistake I see people making is thinking that this subscript here and this subscript here have anything to do with what appears over here. All right, this 2 on the hydrogen and this 2 on the bromine occur because they're diatomic in their elemental state by themselves, right? Over here, they're not by themselves, and we need to represent the actual formula for this compound as a basis of neutral charges. So hydrogen, group 1 of the periodic table, we expect a 1+. Bromine, group 17 of the periodic table, we expect a 1-. And the cheapest, most brute force way to handle coming up with the product formula is to just crisscross, ignore the signs, and this 1 would go down here, and this 1 would go down here, and you get 1 of each, all right? So key things we're looking at here. I don't know what I'm going to make. Let's just pretend. I don't know what I'm going to make. Well, whatever you make has to have hydrogen and bromine, and its formula is going to have to be based on their charges. So the charges are 1 and 1. We get HBr, hydrobromic acid. I was harping on the importance of coming up with showing work for balancing chemical equations in a previous video, so I won't be negligent now as we look at this reaction. We've got hydrogen, we've got bromine, 2 and 2, 1 and 1. Anybody can look at that and say, oh yeah, that's not balanced. And then you can say, what times 1 is 2? Well, 2 times 1 is 2, and that 2 does apply to both species there. All right? So I think that's as basic a synthesis reaction as we can get, and I want to take a look at a few varieties with different charges so we can practice our crisscrossing and reducing, right? And we are looking for a neutral species. That's a real complicated way of saying crisscross and reduce, right? So we've got maybe hydrogen gas and oxygen gas, right? 2 more diatomics. And it's not a trap, but people always trip over this. We've got hydrogen and we've got oxygen, all right? What is the product? Well, your product has to have those things, hydrogen and oxygen. And in this case, it does. Now, to figure out what these subscripts are going to be, we don't look over here. We look at what their charges are. And in this case, hydrogen, group 1 of the periodic table, 1+. Oxygen, group 16, 2-. We ignore the signs and we just put the 2 there. H2O, that's our formula, right? No surprise, right? Water, H2O. And if you note here, I have 2 of the 1+ and 1 of the 2-, so those charges cancel out. In order to balance it, to do our due diligence for showing people what we've done, we'll set up our table of reactants and products again. We've got hydrogen and oxygen, 2 and 2, 2 and 1. So we're going to have to fix that oxygen. We're going to double that side, and that does double our oxygens, but it also doubles our hydrogens, so now we have 4. And we can fix that by putting a 2 right there. All right? So there is another fairly straightforward reaction. And the key thing I want to highlight as we're going on, right? I've got 2 things. The only thing in this case that I can do is make one thing from those, and that one thing has to have each of these, and the number of each of these that we're going to have is based on their charges. This compound here in the second example, it's got to have some hydrogen and some oxygen, and it ends up a 2-to-1 ratio because of the way the charges work out. So let's take a look at a few more examples here. In fact, quite a few more, just to keep ourselves busy. We'll take something like sodium metal and oxygen gas and see what we come up with. Again, don't outsmart yourselves. It's got to have sodium and it's got to have oxygen, right? The question is, what are those subscripts going to be? Don't trip over the idea that this applies over here. That's not happening. This is diatomic oxygen. That's what it is in its elemental state. Over here, it's in a compound, so we're going to run into a different scenario. Sodium group 1 of the periodic table is a 1+, oxygen group 16 is a 2-, so we're going to have a 2 there to make it work, sodium oxide. I'm going to move my reactant product table over here so we can budget our space a little better. I've got sodium and oxygen, 1 and 2, but on the product side I have 2 and 1. So I'm going to double this side, and that'll give me my 2 oxygens that I need on the product side. But now we have 4 sodiums, and we can fix that by putting a 4 right there, all right? And again, the overshadowing idea, do show your work for balancing, because now anybody can look at this and say, yes, it's balanced, right? This is a 2, this is a 2, this is a 2. I guess I never finished that. That's a 2. This is a 4, that's a 4, this is a 2, this is a 2. Look at my negligence in not filling in those numbers. What a hypocrite. All right, let's try another one here. Maybe we'll have zinc and sulfur. Now, there are a few things you need to consider. Like, we know we're going to have zinc and sulfur on the product side. Zinc's a transition metal, and we may not know its oxidation state. It's charged in a compound, but zinc happens to be one that's always a 2+, so 2+, okay? Sulfur is group 16, like oxygen, so it's going to be a 2-. And here we run into a little thing of note, right? Our strategy was to crisscross to get those charges, a neutral compound, and we also need to reduce, so there's a 2-step process there, right? So I'm going to move this 2 down here, and I'm going to move this 2 down here, and then I'm going to say, well, it's a 2-to-2 ratio, that's a 1-to-1 ratio. We get zinc sulfide with a 1 and a 1, right? And you don't have to put the 1s there, but I'm doing that just for show this time. All right, so we'll set up our table of reactants and products. We've got zinc and sulfur, 1 and 1, 1 and 1. It's balanced, right? We don't have to do anything special. Let's try a similar one with maybe calcium and oxygen and see what we get. Calcium, group 2 of the periodic table. By the way, our product has to have calcium. Our product has to have oxygen. Calcium, we're expecting a 2+, group 2 of the periodic table. Oxygen, we're expecting a 2-, right? So we would, again, put the 2, ignore the pluses and minuses, and reduce it so you have calcium oxide, all right? This one isn't balanced, so we'll have to do a little bit of extra work. Reactants and products, we've got calcium and oxygen, 1 and 2, but 1 and 1. Our solution, we need to double that, gives us our 2 oxygens, and then it gives us 2 calciums, and we'll have to fix that over there by adding a 2. If you're still working on completing and balancing, or rather just balancing reactions, what I'd do is pause before I balance these and give them a try on your own, and then you can hit play again and see where I'm going from there. We're just going to keep knocking out a few simple examples, and then we'll look at some more complicated examples, which I think are less intuitive and take a bit more practice. So we're going to try nitrogen and hydrogen, all right? Again, step 1, I don't know what to do. Well, you know your products have to have nitrogen and hydrogen, right? So start by saying, I'm going to have nitrogen and I'm going to have hydrogen. Now, don't fall for the trap of thinking that that and that have anything to do with what goes on over there. This is elemental nitrogen. It is by itself. That's why there's a 2. This is elemental hydrogen. It's diatomic by itself. That's why there's 2. Here they are in a compound. That 2 doesn't apply anymore. So now we're going to have to crisscross and reduce again. Nitrogen's group 15, so we expect a 3-. Hydrogen is group 1, so we expect a 1+. And so if we move the 1 down there and the 3 down there, we get NH3, right? And we are going to have to balance that, not just because we're going to show the work for everything, but because it's not balanced. We've got nitrogen and hydrogen, 2 and 2. Product side, though, we've got 1 nitrogen and 3 hydrogens. I'm going to balance this a little slower just so we can pick up some strategies. When you have balancing with reactants and products tables, my general strategy is just to start at the top and work my way down. Something I'll watch for is if I have any elements by themselves. I think they're good to save for last because I can change them without changing anything else. And then the other thing I'll watch for are odds and evens, okay? And in this particular case, I have an odd number of hydrogens on this side, and I have an even number of hydrogens on this side. And there's no way I can fix that without coming up with some least common multiple. And that's a bunch of words for saying, oh yeah, 2 and 3 are going to meet at 6, right? So I'm going to look at this side and I'm going to say, all right, if I double that, I'm going to have 6 hydrogens, and I'm doing that because I'm going to get 6 hydrogens there. But let's finish here first. There's my 6 hydrogens and 2 nitrogens. That messes up our reactant side hydrogens, but we have a plan, and that plan is to put the 3 there so that we have 6, and now it's balanced, and anybody can see that. The last simple synthesis example I want to look at is maybe magnesium and nitrogen. All right. Again, I think it's normal and important for you to say, well, I don't know what to do. Well, step 1, it's a synthesis reaction. It has to be because you only have 2 different elements. In fact, for all of these cheap examples, it's just 2 different elements, so your product has to have both of those elements, right? I got H and Br, I got to have an HBr. H and O, got to have H and O, right? All the way down. So I've got to have magnesium, and I've got to have nitrogen, right? Magnesium, elemental states of 1, nitrogen's diatomic, so we've got a 2 there. This 2 has nothing to do with what goes on that side. On this side, we have to have an electrically neutral compound, so we'll get that by crisscrossing and reducing, okay? So we've got a 2+, magnesium's from group 2 of the periodic table, nitrogen's from group 15, we've got a 3- charge, and so when we crisscross these, we're going to end up with an Mg3N2, all right? Now, I didn't mention it, but like these charges aren't part of the answer. I would hope no one would mark that wrong, but if you've got any erasers somewhere on your test, you can just be like, all right, well, those are obsolete now, so I'm not even going to write them, right? Just so nobody thinks you're treating them as ions or whatever. So we're only worried about the subscripts. This one also is not balanced. Let's take care of that. Reactants and products, magnesium and nitrogen. We've got 1 and 2, but over here we've got 3 and 2. So we're going to have to fix things, yeah? And all we need to do, if we triple our magnesiums there, we end up with 3. We had 2 and 2, and it balances. Anybody can look at this work and say, yes, those reactions are balanced. Yeah, you can do parlor tricks and just look at a reaction and say, yeah, it's balanced, or I'm going to throw a 2 and a 3 and a whatever here and balance it. But that's not helping anybody, right? In science, we're trying to show people what we've done so that anybody can look at it and duplicate what we did. All right, so those are some basic synthesis reactions. We had a little practice balancing along the way. I want us to take a look at some less intuitive synthesis reactions, and these are based on decomposition, all right? So this is kind of foreshadowing for the next reaction type, our decomposition reactions, because that's where these are going, and they're not intuitive at all to spot. So the first thing I'm going to do is we'll write our example down here, and we'll say we've got calcium oxide and carbon dioxide, all right? We can plan ahead. Like once we know our reaction types, this one looks like what we're going to see as a double replacement reaction. It can't be because we've got oxygen and oxygen and they can't switch places. But again, at first glance, it looks double replacement. So we have to rule that out. It's not. And so what I think it would be wise to watch for in double replacement, all right, and this is a little side note here. In double replacement, you're going to have an ionic compound reacting with some ionic compound, right? In these synthesis reactions, if you see some ionic compound and a covalent compound, it's a synthesis reaction, all right? And if you don't know what it's going to make, you may have to look at the special decomposition reactions. So in this particular case, You can say, well, yes, what gives us a metal oxide and carbon dioxide? That's the decomposition of a metal carbonate, all right? I would say it's very improbable, especially early on, that you would spot that. But what I really want to highlight as we look at several of these reactions is the idea that they're going to look like double replacement reactions, but they aren't. And the way we'll see that they aren't is by saying, we have a covalent compound and an ionic compound, right? Or you could look a little further and say oxygen and oxygen, if they were to replace each other, wouldn't do anything, all right? In this particular case, we get metal, calcium in this case, carbonate, all right, limestone. And the reverse of this reaction is the decomposition of a metal carbonate. You heat it up and you get the metal oxide and CO2. This is how they make cement for concrete, right? CaCO3 is limestone. You can heat it up and get quick lime, which you then mix with water and get calcium hydroxide products. In these particular cases, for the special decomposition, very often they're already balanced, but we still got to show our work, right? I've got calcium, I've got carbon, and I've got oxygen. It's easy to miss that you've got oxygen in two places, so make sure you add them up correctly. 1 calcium, 1 carbon, and 3 oxygens. Product side, 1 calcium, 1 carbon, and 3 oxygens. And anybody can look at that and say, yeah, it's balanced, all right? So general ideas that we're going to watch for there. At this point, not double replacement. I don't know what it's going to be, so it's going to have to be the reverse of some decomposition reaction, and you just got to plan ahead, all right? Another one that might be of interest is, what if we have some metal oxide, again, like cesium oxide, and we're going to react it with water, okay? At first glance, you might say again, oh, that looks like double replacement, except for the fact that we've got an ionic compound and a covalent compound again. And so then it's like, well, I don't know what it's going to make, yeah? You can fake it in a case like this, but let's just pretend we know. This is a synthesis. It is the reverse of a decomposition of a metal hydroxide. In this particular case, cesium, which is a 1+, and hydroxide, which is a 1-. So we just get cesium hydroxide, all right? Now, I say we can fake it, and this is sometimes a strategy I use when all of my other options have been exhausted. But in a synthesis reaction, stuff has to combine, right? So I'm just going to combine that stuff and see what happens, okay? So I've got my cesium, 2 of those. I've got my oxygens, 2 of those. And I've got my hydrogens, 2 of those. All right? And you could look at that and say, oh, that reduces as CSOH, all right? It's not a great strategy, but if you don't have anything else available, it can do if you need to fake it, all right? And it would have worked here as well. In this case, we got cesium and hydrogen and oxygen, 2, 2, 2, 1, 1, 1. And we can fix that pretty quickly by putting a 2 right there. 2, 2, 2. And again, anybody can look at that and see it's balanced. I want to look at another not obvious decomposition reaction as a synthesis, which is something where you have a metal chloride, we'll say lead chloride in this case, and oxygen gas. All right, so this one looks single replacement, and I guess to know it's not single replacement, we don't generally have single replacement with oxygen. I guess that's one place to start. But also, if you see a metal chloride with oxygen, that might set off a red flag that that's a decomposition of a metal chlorate, right? So, not knowing anything else, we might just try and combine things and reduce it. In this particular case, we'll pretend we know our decomposition reactions very well, and then we say, oh yeah, all right, well, we're gonna have a lead chlorate, a metal chlorate, and in this case, lead is a 2+. And if you didn't know it, we can fake it by just putting that 2 up there, right, uncrisscrossing it. And we've got lead in this case. Chlorate is ClO3. It's a 1-, so in order to make this work, we'll need 2 of those, yeah? We can set up our balancing table here with lead and chlorine and oxygen. We've got lead, chlorine, and oxygen. On the left-hand side, 1 lead, 2 chlorines, 2 oxygens. On the right-hand side, 1 lead, 2 chlorines, and 6 oxygens. Oops, I don't want that right there. and 6 oxygens. So be very careful. This subscript does affect both pieces inside. That's 2 chlorines and 6 oxygens. All right, it's not balanced if you didn't notice. The leads and the chlorines look good. Oxygen's no good, but we can turn a 2 into a 6 by putting a 3 there. All right, we end up with 6, and it's balanced, and anybody can see that. I have 2 more that I want to glance at, and we're going from not very intuitive to really not intuitive, where we pretty much have to fake it. All right, so setting this up, I'm going to put another line here. These are special decomposition reactions, and then this is these are the synthesis version, the reverse of some specific decomposition reactions. And right here, I'm going to put the reverse of some specific decomposition reactions, specifically decomposition of oxy acids, all right? These are not intuitive at all, but let's give it a look, and how might we spot them is another thing we're looking for here. In this case, we'll start with maybe like H2O and SO3. Versions of this reaction were like a huge deal back in the day, and they're still important, but they are taken care of because of regulation a little closer. But as we look at this one, we've got a covalent compound, right, and a covalent compound, and we're going to have to combine them. And like, when all else fails, just combine stuff, right? So in this case, I've got H, 2 of those, S, 1 of those, and O, 4 of those, right? And it's H2SO4, right? We've faked it and we got H2SO4. That's sulfuric acid. And we can set up our balancing table with our reactants and products. We've got hydrogen, sulfur, and oxygen, 2, 1, 4. And on the product side, 2, 1, 4. And that works out well. In general, like if you're setting up, how do I know which elements go in which order? Big picture, it doesn't actually matter. Anybody could look at it and know what you're talking about, but if you want to get technical, the most common way you'll see these is like increasing electronegativity, right? So hydrogen's at 2.1, sulfur's at 2.5, and oxygen's at 3.5 in terms of electronegativity. Or you've got like lead, then chlorine, then oxygen. That's not anything that I would bother remembering, all right? Generally, give them in whatever order you want to. You would start with cations where possible, and if you can spot a polyatomic ion, make it look like one, right? SO4 is sulfate, so you can watch for that. The reason I say it's semi-relevant is that on the south side of Lake Michigan, at northern Indiana and southern Michigan, there used to be all kinds of steel mills, and they would burn coal in the steel refining process. And when you burn coal, there's a bunch of sulfur in dirtier coals, which then turns into sulfur oxides, very often SO2. And this is something people don't think about, but like if you have coal, carbon, and it has some sulfur in it, well, the carbon oxidizes to CO2, and the sulfur oxidizes to something like SO2, right? So when that SO2 or possibly SO3 would go into the atmosphere, and there's moisture in the air, it could then rain down as acid rain, okay? Not necessarily sulfuric, but maybe sulfurous acid. Or you could get some nitrogen-based precipitation as well. But it was a big deal in northern Indiana because these sulfur oxides would go up into the air and blow across Lake Michigan to Canada and then rain down on Canada. And boy, were they upset. And justifiably so. So the EPA put a bunch of regulations in place to prevent things like that. The last one I want to look at here for our single replacement reactions is another synthesis of an oxy acid, the opposite of our decomposition of an oxy acid. And we'll take H2O, right? And we'll say we've got something like NO2, all right? In fact, I want to do, that's fine. I'm sorry, I want to do N2O5 for this one. And we end up, in this particular case, if I just combine everything, right? I don't have an ionic compound and a covalent compound. I don't have something that looks single replacement but has oxygen. I have 2 covalent compounds, so I've run out of options. I'm just going to smash them together and see what comes out. I know I've got hydrogen, 2 of those. I know I've got nitrogen, 2 of those. And I know I've got oxygen, 6 of those. So if we write that out, we've got H2N2O6, right? And I think most people could look at that and say, oh, that's going to reduce, right? HNO3, and that's nitric acid, okay? And if we set up our balancing table here, reactants and products, we've got hydrogen and oxygen and nitrogen, 2 hydrogens, 6 oxygens, and 2 nitrogens. And on the product side, we've got 1 hydrogen, 1 nitrogen, and 3 oxygens. So if we put a 2 there, 2, 6, 2, and we're all set. And I think that in the big picture, in terms of like what do you need to know for synthesis, whatever you're starting with has to be combined into something over here. To get the formula over here, generally you're going to crisscross and reduce. That's the basics of synthesis. So if you can remember that, take this stuff, stick it together, crisscross and reduce. That's the basics of synthesis reactions.